Jarly, welcome to our faculty and your students.
Okay, thank you very much for the introduction, Paul. Yeah, so as Paul says, I'm Norwegian. My Spanish is hablo portugués, mas o español da poquito mal. So if you have questions, try to ask them in English, but I might understand what you're asking in Spanish as well. Perhaps. Okay, so what I will try to do is to give you in 1 week a course I normally give to master students over 6 months. Okay? So I'm going to go a little bit easy over some of the difficult concepts, but I think it's possible to understand most of this course even crammed into 1 week. So we'll see how that goes. The big difference is that when I teach this in 6 months, I do almost all of it on the blackboard, and I cannot write that quickly. So we're going to do most of it using slides. So I'm going to start with a couple of things. First, some information for all of you, which is a couple of useful pieces of information. Firstly, all the lecture notes, so all the slides are already on this web page. Okay? And it will also contain all sort of small problem sets. I'll explain that in a second. But this web page then has everything that you should need for this course. It also has a set of proper lecture notes for this course. So there are 200 pages or so of lecture notes that give more background than what I'm covering. Now, the problem sets, there are two things. So some of you take this course as part of your lectures, as part of you want to get credit for your course. And the problem sets are divided into two. So I can show you just an example of this, just for a second. The one I put down on today. I'll try to remember to open the problem set and not the solutions. Okay, so this is the first problem set. Okay, it has some background information, and then it says on top here, go through problem, and those are problems that I will tomorrow I will explain these problems in the beginning of the lecture tomorrow morning. Okay, so these ones you can do, and I recommend that you try to do these problems, but I will cover them tomorrow morning. Okay. Otherwise, there are 2 of them, and you can look at them if you want. Then there are 2 here, which has hand-in problems, and those are for those of you that doing the course for credits. So you actually have to solve these 2 problems and send it to me, the solutions, electronically. Okay, so that's what I have here. Okay, and there will be 1 set today, and 1 tomorrow, and 1 on Thursday. There will be none on Friday because I'm gone on Saturday. The deadline is in 2 weeks, more or less. And this is my email. Whoops. No, but I'm sturdy. I'll teach on this side. So okay, so this is the situation for the grading for those of you taking the course. So what I'm going to start with is I'm going to try to explain to you what we want to learn from this course. What's the point of what I'm doing? Okay? And to do that, I'm going to talk a little bit about observations of galaxies. So if you have any questions or anything that you find unclear, I'm speaking too fast, I'm speaking too low, just put your hands up and shout at me. So basically the story of this course is to go from a uniform distribution the way that these chairs probably at some point in the past were distributed in this room. So there was a nice set of chairs in rows, and there were a regular grid of chairs. And then as students come, this chair starts to cluster together, and you get these collapsed clumps of galaxies or students. And we're going to try to see how that works overall. So in many ways, the population of galaxies that we see in the universe consists of two broad types of galaxies. One is the class of galaxies that we typically call spiral galaxies or disk galaxies. They often have a lot of gas. They're not only stars. They often form stars now. So there are many young stars here. So are showing up as the blue light here. And most galaxies are not alone in the universe. There's nearby galaxies around it. Around our galaxy is, of course, the Magellanic Clouds. One of the more imperialistically named clouds. And we have the elliptical galaxies that are typically more massive. They typically have less gas in them. And they typically have no active star formation going on. So when we look at these in terms of color, these are blue and these are red. And we would like to understand whether there's anything they're related to each other. The way we often do this is by classifying galaxies. We put them in, we look at their images, we look at their structure, and we see where stars are distributed. And this is a famous diagram called the Hubble tuning fork, where elliptical galaxies are here, spiral galaxies that are very symmetric are here, and spiral galaxies with a bar in the middle, called barred spirals, are here. And this plot taken from a paper by Lee et al. Shows how this changes as you go back in time. So this is 4 billion years ago, this is 11 billion years ago. Remember, the universe is about 13.5 billion years, 13.4 billion years old. So this is close, this is 2 billion years after the Big Bang. And you can see the galaxies change a bit. And how does that change happen? And we can summarize that appearance in terms of taking in a azimuthal average. So we take a line out here, and then we average in circles or ellipses. And we find that the light in these spiral galaxies drop as an exponential, e to the minus r. And in these galaxies, they typically drop off in slightly more extreme way, so where this, or a slightly different way. They are very often sharply peaked in the middle and have long tails of light going far out.
Sorry, John.
Yeah.
Intensity.
This is an intensity function. Yeah, I didn't put on. This is the luminosity per small area. So it's an intensity per area. So if you want to integrate it up, it needs to be multiplied by 2 pi r. And galaxies are not very simple. Okay, so stars show very often nice relationships, and I'll show you some in a bit. Galaxies, if you plot this is a plot that shows the mass of the galaxy, or the amount of stars in the galaxy, in logarithmic units. So this is like 10 to the 10 solar masses. Our Milky Way is around here. Okay, this is about the Milky Way. On this axis, it's the amount of stars per kiloparsec, is the density of stars in the galaxy. Okay? So if there was a nice mass density relation for galaxies, which we might hope there would be some tight relationship here. Okay? If you plot this for a star, you might find something that's useful, depending on the type of star you plot. But the galaxies don't show any reasonable relationship. It's complete scatter, except here. These are dinky things, and if you look here, they are not galaxies at all, they are globular clusters. So globular clusters, there is something that you could call a mass density relation, but for galaxies, not so much. So it's a very diverse population, and it's not obvious that you can easily explain what's going on here. So the way we have done this for a long time is you can think about a galaxy being characterized by many numbers. Okay? It's a multidimensional distribution function. It's a function of its amount of metals, the amount of stars that are being formed, the amount of stars that are already in the galaxy, the amount of gas that's there, maybe something to do with its dynamics. Is it rotating? Is it chaotically distributed in terms of dynamics? And there are lots of these parameters. We don't know how many parameters are needed to explain a galaxy. Okay? It's not an easy number to define. But what we can do, we cannot observe this. It's too complicated. What you can do is you can take this many-dimensional function and you can project it down onto some axis. And so that's what we have done. And whereas this is a royal we, it means that I have not done it, but I say we anyway. So the Tully-Fisher relation relates the luminosity of a galaxy to its velocity, rotational velocity. So it says if it rotates faster, it's going to be brighter. It sort of makes sense. But the Faber-Jackson relation is the same relationship, but now for elliptical galaxies, not spiral galaxies. This is for spiral galaxies. This is for elliptical galaxies. This is not a rotational velocity because elliptical galaxies do not rotate much. They have chaotic orbits, so they have a dispersion of velocity. But it's very similar power law. So we'll see later in the course perhaps some way of explaining, or at least get some insight into why this looks like that. The fundamental plane is another one we'll look a little bit at in a problem set, which relates the size of a galaxy to its dynamics and to the density of stars, so density of light, and some constant that we don't really understand. And then there is a relationship we are going to spend some time on, and I'll return to very shortly, and that's the relationship between star formation rate and stellar mass in galaxies. Unfortunately, this has become known in literature as the star formation, or the galaxy main sequence. And everybody used that name, and I think it's absolutely appalling, because the main sequence has a very clear meaning in astronomy. It's the main sequence is something that stars live on. And the galaxy main sequence has nothing to do with that. So it's a bad name, so I call it the star forming sequence. So ideally, we would like to understand all of this, and we're not going to do that. But we're going to understand some of it, and we're going to focus quite a bit on this one, because it's quite a striking result. But to understand these relationships, it's also useful to understand how we can get the information that I'm going to give you. So let me show you an example here. It's one of the times I need to be at my computer. So what I have done here is I made a small movie that shows the distribution. So let me see if I can start it and then explain it. Maybe that will be the best. Okay. Okay, so what I'm going to show you what's happening here is the distribution of light in a galaxy as time goes on. So what I'm going to do is I'm going to start with a big galaxy. I'm going to form a lot of stars. And then I'm going to let that star formation rate, so the rate of new stars being born, is going to decline like an exponential function. Okay? So it's going to take 6 billion years, and then it basically stops forming stars. And what I'm plotting here is basically the wavelength and the flux in CGS units, some arbitrary normalizations, but it's energy per unit wavelength. Yeah.
This is not real galaxy.
No, this is a model. And so all of this is a model, and all these emission lines that come in here is an idealized model for the galaxy. A real galaxy might not look exactly like this. It has some model parameters up here, but I'm not going to go into details. What I want you to just focus on, there are two different things you should see. Okay? Now, this is the rate of star formation. Here it's very high, and you see these huge emission lines, strong lines. You see those lines, you know, wow, this galaxy is forming a lot of stars. Okay? You can convert from this flux in this line to how many stars are being formed, almost directly. I'll come back later exactly how that happens, but that's the first thing you need to think about. The other thing you notice is that as this goes down, the color of a galaxy is the amount of flux here. Whoops, I shouldn't shadow it. The flux here relative to the flux here. Okay, that's red, that's blue. Okay, so as time goes on, you're going to see this thing will change shape, and that means that it will change color. I realized just a bit too late that I should have put that on the movie, but I didn't have the time to fix that. So let's see what happens. Now you see, this is very young. It's only a few million years old, 10 million years old, and now you see the shape changing. Okay, now the color is starting to change. The lines are less prominent because the star formation rate is lower. Now you can just about see it here. And as you get close to 6 gigayears and the star formation rate has gone down 1 e-folding time, it will really start dying off. And this part, which comes from young stars, which I'll show you in a second, is dropping down more than the bit in the red. Okay. So let me also show you then what kind of stars contribute in these places, because that also teaches you what you can get out. So here is almost the same plot, but what I've done here is I've colored each wavelength bin with the luminosity weighted effective temperature. Okay, so here you can see the temperature in 10,000 Kelvin, so 40,000 Kelvin, 20,000 Kelvin, 5,000 Kelvin. And that's the temperature of the star that dominates the light here. Okay, so remember the sun is about 5,000 Kelvin-ish, so that will be reddish. So when stars like the sun dominate the spectrum of a galaxy, then you see it be red here. Here, in the ultraviolet, this is 100, whoops, this is 1,000 angstrom. So this is close to the hydrogen ionization limit, or the Balmer limit. Here, you will notice that all the stars that dominate here are young. They're really hot stars. It's the only thing that you will see there. Okay, good luck. Okay, there we go. So now you see here, things change quite quickly. Even after 10 million years, it's a huge difference. The ultraviolet still probe very massive stars, but you can see in the red, at 2 micron, stars like the sun are starting to dominate already when you are just less than a gigayear old. And so now you can see this is what happens. This is actually what the stars are. When you look at the energy distribution of a galaxy, you'll see, look at this end, you see stars like the sun, and they might be really old. They could easily be 5 billion years old. And on this side, you look at stars that don't live more than 10 million years. Okay? They explode like supernovae. Most of them anyway. And then there is a transition regime, which is harder to understand. But what you can take away from this is that temperature and age of stars are, of course, closely related. So if you look here, you look at young stars, and you're really probing that kind of stars, and as you move out in wavelength, you will touch on different types of stars. So by comparing these observations here, and observations here, and here, you can start understanding what's the makeup of a galaxy. And that's the physical reason why some of the tricks that we're using actually works. And the most famous example of this is probably what's called the bimodality relation. And so here is from something I created from the Sloan Digital Sky Survey. This is the mass of galaxies. So the Milky Way, again, is about here. And here on this axis, it's the color, the U minus R color, so the difference in light at, say, 4,000 angstrom to about 6,500 angstrom. And you can see there's 2 clumps. It's the red sequence, and there's the blue sequence. On the blue sequence live spiral galaxies, mostly. Down here, there's some stuff we call irregular galaxies as well, which is a bit of a mess. One can talk about them. And up here are typically elliptical galaxies. Mostly it's elliptical galaxies. And this is a very striking relationship. Does that mean that galaxies go from here, go up in mass, and then they jump up here? Is that what happens? We don't really know. And so try to understand that. What people have done is they try to trace this back in time. So if you look at this relationship back in time, this is from Whittaker's PhD work, here is a slightly different, there isn't precisely the same plot I showed you in the literature, but this you can think about is close to what I called mass earlier. Okay, so there is a red sequence and there's a blue sequence. And here I go back in time. Here I'm about half the age of the universe. Yep? So it's typically elliptical galaxies. Yeah, round spheroidal galaxies. Exactly. And so they live here. Okay? And then the spiral galaxies typically live here, and then you move up out in redshift. You're back in time. Here you're really high redshift. This is only 4 or 5 billion years after the Big Bang. Here even higher. Here you're about 3 billion years after the Big Bang. And I don't know what you see here anymore. But here at least you can see a hint of a sequence here and a sequence here. So this difference still exists even at very, very distant universe, which is quite striking. Another observable, which we will spend time on here, because it's quite important, is what you can call the distribution of masses. Okay. So if you took a volume of the universe, you just took a box of the universe, that's say a megaparsec wide, a megaparsec deep, a megaparsec tall, it's kind of inconvenient to handle, and you just pick a galaxy at random inside that box. What kind of galaxy will you get? You will get a dinky, completely boring, uninteresting galaxy. That's what you get. That's what almost all galaxies in the universe are. They're very small. And this is how we encode this. It's called the mass function of galaxies, and it's probably one of the things we really, really want to understand why it looks like this. So here is the mass of the galaxy in solar masses, log solar masses. Again, the Milky Way is about close to the knee of this function. And on this is the number density. So it's the number of galaxies per cubic megaparsec. So it's counting galaxies. And what you can see is that this function, it's certainly not constant. This is logarithmic, and this is 10 to the minus 6 to 1. This is 6 orders of magnitude, 1 factor of a billion. And typically the function, and we will come back to this, you don't need to write this because I'm going to bore you with this function later, but the number of galaxies at a given mass is proportional to let me just call it something else. It's proportional to a function. This function is very well described by this functional form. So a power law and an exponential cutoff. Okay, so there are two ingredients. This is the power law, and this is the cutoff. And there is a knee, which is where the Milky Way lives, and that's the transition zone between those two. Why does it look like that? And why is it so universal? Everywhere we look in the universe and we look at galaxy mass functions, they look more or less like this. Okay, so that's a curious result, and we would really like to understand what that's telling us. A final result, which I'm not going to talk about here in the course because I don't have enough time for that, but it's still a very important constraint on of the history of the universe, is the history of when stars formed in the universe. So you can do that in two ways. You can use the archaeologist approach, and you can go around and dig up. So you can go to the Milky Way, which we live in, and you can count stars of different ages. And then you can build up a picture of when did stars form in our Milky Way. That's called galactic archaeology. And you can use that to extrapolate going back. And that's very powerful, but it's difficult because again, a star that's 10 billion years old and a star that's 12 billion years old, or a star that's 8 billion years old, they actually look very, very similar. it's very difficult to say that this is an 8 billion years old star, and that's a 12 billion years old star. So you kind of get a bit blurred. It's like I take off my glasses, I can't see. I can't distinguish the stars in the high redshift universe. So what we do instead is we go to galaxies, we see them in the distant universe, and then we count them. And so that's what people have done here. So this is probably the best one. This is the age of the universe on the axis here. Unfortunately, too small for you to see, but I'll read. This is 10 billion years. It's close to today. Today is at the end. And this is 600 million years. And this is the Big Bang. This is a logarithmic scale, so the Big Bang is somewhere else. But what you can see is that the star formation rate, the amount of stars being born in the universe, is quite low now. And then it was higher and higher and higher in the past until there was a peak. That peak was around when the universe was between 2 and 3 billion years old. That's when most of the stars in the universe were born. Okay, that's an interesting result. And then it dropped off. And we would like to understand, why does it look like that? Why do you have this transition between a decline now and a rise in the past? And why was there a rise? Why didn't stars form at random times? Or why didn't they all form in the beginning? There was a lot of gas around in the beginning. Why did it take a long time, 2 billion years, before most of the stars formed? Okay, well, this is a bit out of order. I must have moved this. But this is just going back to what I said earlier about what kind of galaxy do you get if you pick them at random. And so this shows where most of the mass is. So most of the mass is distributed in this red line. It says most of the mass, most of the stars in the universe, they live in galaxies that are pretty much like the Milky Way. So galaxies like the Milky Way contain almost all the stars in the universe. But most of the galaxies, this black line, most of the galaxies are very, very low mass galaxies. They're dinky galaxies, but they don't contain hardly any stars. And sometimes it's difficult even to know that they're galaxies. You look at them and you can count 10 stars. So you might then ask, why is that a galaxy? Well, it's difficult to know. And this is the size. The sizes of these are also very, very small. Now, I said I would go back to talk a little bit about star formation rates, because we will use that. So what I said earlier was that you saw these emission lines in my movie. And so why do they measure the star formation rate? Well, first, you need to think about what can you actually measure. So stars have a variety of masses. Okay? So you cannot, in the distant universe, you cannot see the effects of a dinky star, like something like the sun. It's just not bright enough. So what we do, if you think about this as the mass distribution of stars, so mass of star, number of stars, and the distribution is a power law. Okay? Depending on the different models, it has different slopes. It doesn't matter what it is now. So very few stars have very high mass. So let me put down here like 10 solar masses. And stars that are more massive than 10 solar masses, depends a little bit on the metallicity and stuff. But it's not so important, the details for what we're doing now. So if they're more than 10 solar masses, the crucial thing is that they produce a lot of photons that with energy above 13.6 electron volts. So we take Q, H, it's the number of photons energy around 13.6 electron volts. So different people define this in slightly different ways, and they can be an integral to infinite energy, or it can be just a small wavelength range. It doesn't really matter. And so the idea here is 13.6 electron volts, you remember, is the ionization energy of hydrogen. Okay? So these can ionize. And that's crucial. There's a lot of hydrogen in the universe. These stars, they can ionize that hydrogen. And when that hydrogen then recombines, when the electrons recombine with the protons, they give off these emission lines that you can see in the spectrum, which have a bunch of different names. So you have the Balmer series, H alpha, H beta. You have the Passion series, the Brackett series. And in the ultraviolet, but that's harder to work with, there's the Lyman series. So crucially, that the luminosity of a line like that, so means that the luminosity of, say, H alpha is going to be proportional to the number of ionizing photons with energy above 13.6 electron volts. And that can tell you the number of stars with mass greater than 10. There's a missing 10 there. 10. Okay. And so then, now you can wag the dog by the tail. You know the integral of this function from 10 to infinity, or 10 to 100. And now you can extrapolate to the whole function. And that's what we do. Okay, we take the tail and we wag the dog. And it usually works. And so that's the trick. Okay, that way you can go from recombination lines to the amount of massive stars and figure out the star formation rate that's happening. There are other lines that you can use as well. This is a bit more complicated to explain, like like forbidden lines like oxygen 2, but generally that works. The other way you can do it is to go back to that other movie I showed you, which showed that in the ultraviolet, most of the stars that dominate in the ultraviolet are really short-lived. So again, the same trick. You can use the ultraviolet light. You can then, from that, say how many massive stars there are, and you can estimate the star formation rate of the galaxy. So that's the ultraviolet. And finally, if there is dust in the galaxy, these stars, they heat up the dust. So the dust works like a bolometer. You heat it up, and it's radiated away. And then you can measure this radiation, and you can then infer how many hot stars there are inside your galaxy. And I think I won't go through the galaxies part. And now I misplaced my remote control. And so here is a comparison of this observation. I think that's a bit small. Just give me a second. Okay, so here's the same galaxy. It's the galaxy M51, famous spiral galaxy not very far away from us. And here, this is the luminosity of that galaxy in this H alpha line. So in that line, recombination line of hydrogen. And everywhere where it's bright, stars are being formed. And you can tell by looking at this image how many there are. This is the same, but in the infrared. This is the dust that's being heated by these stars. And you can see that except for the fact that this telescope, the Spitzer telescope, was quite a small telescope, so the image is a bit blurred. But otherwise, you can see there is a one-to-one match here. You can see features are going to be the same in those two images. And that's because they're both tracing the same thing. And these two show where the gas is located in the galaxy. Okay, so now we know how to, well, kind of. I skimmed over quite a few dirty secrets, but you don't want to know. So let me just move on to what I call the star formation main sequence. Or what I didn't call, but other people do call. So this is a little bit confusing plot. I'll show you another version in a second. Again, here is the mass. And here is the rate of star formation. So the number of young stars being born in this galaxy. And what you see here is there is this remarkable sequence here This is this thin bright gray shows the scatter around the scatter around the average line, and the blue is a fit to it. These galaxies is what we call the red sequence, the elliptical galaxies. They don't form stars, so they're not. These are upper limits. They're somewhere below here. So I'm ignoring them. Makes my life much easier. But this relationship is quite tight. There's very little scatter in this. And it's a power law. Star formation rate goes as this amount of stars to some power, which is typically a bit below 1. And another thing that's crucial, which is essential for us here in the course, is that if you look at the same relationship, but you now go back in time, it doesn't stay the same in normalization. So here is the present-day universe, more or less, kind of. Here, a bit further back in time. Here, a bit further back in time, and even further back in time. So this is about half the age of the universe. This is about 6 or 7 billion years from here to here. And what you see is that this relationship, it just moves up. It doesn't change very much. It doesn't suddenly flip slope. The slope is consistent with being the same, but it moves up as you go back in time. And that's, of course, because more stars were being formed earlier in the universe. So that's what you see here. But why does it go up by that amount? I mean, I can wave my hands and explain why it should go up. But what's important is to understand quantitatively, why does it go up by that much? Okay? I don't care. I mean, it's fine when I give a popular talk to explain in a hand-waving way, saying, "Ooh, it goes up because there's more gas in the galaxy." But that's not good enough for you. Okay? You need to understand quantitatively, why does it go up by a factor of 2, 1.5? I don't know. So this is essential. We will try to understand this one. The elliptical galaxies I will not say very much about. They are very, very important in many ways. And this, it was a bit difficult to cut this one. So the main focus of this one is really the left panel. So this shows, as a function of the mass of the galaxy, when did most of the stars form? Okay? So when you go down to, say, Milky Way, you say most of the stars, they formed, say, 6 billion years ago, 5, 6 billion years ago. That's very satisfying for the Milky Way because it satisfies the Copernican principle that we are not special. So the sun is about 5 billion years old. It was formed when most of the stars in the Milky Way formed. So we're not special. Well, not in that way at least. But galaxies that are much more massive, say 10 to the 12 solar masses, they formed almost at the beginning of the universe. Which is surprising, because you would think, oh, it's the biggest thing, it should take the longest to form. But no, it's the other way around. It's the biggest things form first. This, explaining that, is a bit complicated. And so we'll probably skirt around that. I don't think I will have time to go through that particular aspect, but we'll see. Depends a bit. But we do understand more or less why that happens. And it happens because these galaxies form where there is the most matter in the universe. So if you have a lot of matter, that's when they form quickly. Yeah.
The right side of the shows the peaks of formation at different redshift.
Yeah.
Why do you have 2 peaks for red and for blue?
So that's why I should probably cut that one out because it's a bit confusing, but it doesn't work very well. So what these ones show is actually what goes in here. So this is taking just the galaxies that went into this part of the diagram, and you take all the stars that went into those galaxies, and you say, when did those stars form? And you find that those stars, they formed with this distribution. So most of them formed around here, so it corresponds to this average value. And then this is a distribution. So some stars formed early, in the center of the Milky Way, there are lots of old stars. In the halo of the Milky Way, there are some very old stars. And this is the same thing, but for the massive end of the galaxies. And so here, you see most of the stars formed quite a long time ago, but some formed also quite recently. So it really is really the 2D distribution that went into this error bar, but put in here. It's a bit confusingly plotted. It would be better to have it in 2 plots, but since it's not my data, it's not easy to do. But it's interesting, actually, it's actually kind of amusing to look at this. So you say, okay, a lot of this progress has happened in the last about 10 years. But actually, if you go back quite a long time ago, so there's a famous astronomer that died, unfortunately, way too early, Beatrice Tinsley. And she was the first person to really develop the idea of how galaxies, or how the stars in galaxies formed. And she had, I mean, today she is brought up as one of the leading lights of galaxy evolution, but at the time she actually had major problems because people thought what she was doing was a bit wacky, a bit crazy, and didn't believe that it was possible to do. So she had trouble publishing her papers, she had problems getting a permanent job, etc. Eventually she did get it, and she did eventually become very recognized. But it's really striking to think, you know, this is what she did in 1968. She plotted, this is something related to the mass of the galaxy, but it isn't really, but it's a particular type of galaxy. And this is their, these are different masses of galaxies. And this is age of the universe, okay? And this is something to do with the star formation rate in these galaxies. So this is what sort of maybe one of the iconic papers for star formation histories. It didn't come out as nicely as I thought. From a Nature paper in 2004. Remember, Nature should only take papers that come with new results, and they should ideally be wrong. But this is what they published. Okay, these are different masses of galaxies and age of the universe. And they showed that more massive galaxies formed early, which is what I showed in the previous plot. But now look at what happens if I just flip that one around. Now you can see these curves. They're very similar to what Beatrice Tinsley managed to get in 1968. So there's nothing very new under the sun.
She was right.
She probably was right, yeah. She was right in most of the things she did, actually. But, you know, it's still, it was a fancy method. It was a much fancier method that was used to get this plot. So. Okay, let me skip over this one. Well, let me touch on this very briefly. We won't have very much time to talk about galaxy mergers, which I think you did last week with Simon. But what we really think the universe is hierarchical. Hierarchical universe means that small structures forms first, and then they merge together to make bigger objects. And we often show this as a merger tree. And so here, the width of these branches depends on the mass of the object. So you have small objects, and then they crash together to build bigger object. And then they build up and build up and build up, and they make a big galaxy in the end. And you can go backwards, and you can see where things came from. Okay, this is a theoretical construct. We cannot measure this, because then you would need to see the same galaxy many times in the past, and that's not possible, unless somebody invents a time machine. But these mergers are nice for two reasons. One is that they give beautiful images that you can show to the public. Here are some examples. But also because they are how you build up galaxies. So galaxies are built up using these mergers. And when that happens, you get a burst of star formation rate. That's not very strange. You have a bit of gas. You have a bit of gas here. You push it together. The densities will be higher. You have a lot of density. And stars form when the density becomes high, so you can cool down, and you form stars. So that's what happens here. And this, you can measure this. So here, is the star formation rate in galaxies depending on how far apart they are. This is 400 kiloparsec, and this is 0 kiloparsec, then they are on top of each other. And this is the difference in star formation rate between a galaxy that has no neighbors and one that has a neighbor that's 100 kiloparsec away, 50 kiloparsec away, and 10 kiloparsec away. And you can see when they're really close, like 30 kiloparsec, then the star formation rate starts to go up quite a bit. So in some 4 billion years in the future, when the Andromeda galaxy comes close to the Milky Way, we will see something like this. We will get more stars being formed in the Milky Way. We probably will not be around, or at least I won't be, but hopefully humanity will. And there will be a slight increase, but it is not very large. Okay, so here's a summary bit, which I'm just going to leave here because you have this written down in the slides, so we can skip over that for now. Now, I don't know, maybe yeah.
You will put the slides at this website.
Yes, so all the slides are on the website already. So, so if you have Wi-Fi access, you can. I'll bring up the web page again at the end so people can get it. Not sure whether we should have a short break, or is that usually how do you usually do the 2 hours in one go, or do you usually have a break?
No breaks.
No break? Oh well, then we'll go on. Then I'll be ready for lunch when I'm finished.
We'll do the break at
Yeah. Well, I'll do the break when I'm finished. Okay. So I heard some comments about the people that do cosmology being here. I'm not going to talk much about cosmology. Okay, I'm going to stay away from relativity most of the time because we don't need relativity to understand galaxy formation, not very much. Okay, so you won't have to calculate Christoffel symbols, you don't need to do general relativity, etc., but you still need to know some basic facts about cosmology. And that's because galaxies live in the universe, and the universe changes. And that matters. So let me start out with a cartoon. I'll straighten up the cartoon a bit later, and then particularly in the second lecture today. So the cartoon is basically that the universe started, or at least the earliest time we can get some information about, is the Big Bang. Okay? In reality, our current observational data allows us to go back to about, say, 3 minutes after the Big Bang. Okay? Or well, a little bit further. But in principle, our physical laws, if they all function, then they should all function back to some 10 to the minus 30 seconds after the Big Bang. After that, it's anybody's guess. The Big Bang is the starting point. There is a period probably when the universe expands very, very rapidly, called inflation, and that sets the initial conditions for differential equations that govern the universe. We can see that in an afterglow called the cosmic microwave background, and that's about 300,000 years after the Big Bang. And so if you want to look beyond that, so that 300,000 years from the Big Bang, that's effectively like a photosphere of the universe. Beyond that, you cannot see earlier directly. Right? It's like in the sun, you cannot look beyond an optical depth of 1, effectively. That's as far back into the sun that you can directly see. You might be able to infer things further away using helioseismology, for instance, and that's what we have to do as well. We have to use indirect ways of find out what happened before that. Then there was a period when the universe was boring, very boring. There wasn't very much happening. It was basically consisted of hydrogen and helium, and it was just sitting there, not doing very much. And that's called the Dark Ages. And we know very little about them, and we hope to understand more. And then, at some point, the first stars formed. We don't know when that happened. We hope that in some years we will have some observational probe of it, but it's hard to know. And then at some point, the first galaxies formed. Right? Galaxies being more than one star. We think, but we don't know, that in the beginning, you typically formed single stars, big single stars. Eventually, there were enough of them together to create something that was gravitationally bound. And then you got a galaxy. And that happens somewhere at redshifts of about 10-ish. And after that, you really started forming galaxies. And so in the lecture course, we will end with that. We will end with the beginning. And this whole evolution is complicated. But it's not complicated if you get rid of all the gas. So if you get rid of everything that makes us what we are, then the universe is easy to solve. Okay, it's completely uninteresting because we're not there. But if you only include dark matter, so things that are not baryonic, you ignore radiation, you ignore baryons, you ignore everything that we know, you just include the stuff we don't understand, then you can solve the universe, which is kind of ironic. And it shows an evolution like this. This is at an early age. Sorry, this particular shot is at the present day. This is the end result. This is one of the more famous simulations being made. Let me show you how it evolves. So, okay. Oh, oops. Okay, I included the wrong movie, but okay, that's... Let me just show you this one. I can't change that very quickly now, but this one shows another point. What I was going to show you was one movie which starts completely uniform and then eventually gets close to the, gets more and more structured formed. Okay, I'll show you that tomorrow instead. But what this one shows you is what the universe looks like in dark matter today. And what it shows, this is a big scale, okay, that's a gigaparsec. A gigaparsec is big. That's basically the only thing you need to know about that. But now you zoom in, and what you can see is that there is structure on all scales here. And it's very filamentary. There's lots of structure in streams, lots of structure in clumps, and some big clumps, and these clumps are connected to other clumps with streams of dark matter. We know how to do this. We know how to calculate this. And after last week, you can probably do this, not as big as this, but you could do a simulation like this. There really isn't that much more to it. Okay?
We saw this Millennium movie, including music of Pink Floyd. It's better.
Yeah. Yeah, now you have my boring commentary instead. Yes, that's right. So this is zoomed in over a cluster of galaxies. It's the biggest structure in our current day universe. And the crucial bit here is that you have structures on all different scales. You have from big scales to small scales. And if you, instead of looking at this in this way, now let us stick ourselves to a galaxy. And we see what the things look like for that galaxy. Why doesn't it want to move with my remote control? Let's see if that works. Okay. So now we're staying on a galaxy, and we're seeing what happens. Ah, interesting. We're not seeing this because it's not working today. This is... Okay, I'm not going to sit here and do that. I don't know why this is not working like that. Give me a second. I'll have to open that up some other way. Okay, let's hope this works on its own. If it doesn't, okay. So what you see here is how galaxies might pass through the volume around this galaxy, and you see they are slowly collapsing down here, but here it's a spiral galaxy that's in the vicinity, which eventually will start interacting. This is a bit sped up in terms of time. And I think I opened the slow one. Gee. Okay, so that was one merger. There was another merger. And you see, after the merger, it has formed a slight bar. And then as this thing goes on and on, it slowly builds up and builds up mass, and it becomes a bigger and bigger spiral. And part of the interesting thing is it builds up from the outside. Okay, so it adds things on and it becomes bigger and bigger. And sometimes it just changes morphology completely. Now, unfortunately, I opened the really slow version of this movie. They're all the same name, and they're just some weird extension. So I'm not going to run this the whole time. It's going to take far too long. But we will come back to these movies in Thursday's lecture, because they are crucial for understanding how spirals form. Okay, so let's just look at the history of the what's called the thermal history of the universe. So how did the universe evolve as a whole? So if you go really far back, the temperature of the universe was hundreds of thousands of Kelvin. And remember, the only thing that's in the universe, essentially, is hydrogen and helium. And they are both going to be completely ionized when the temperature is that high. So the only thing you have is a soup of protons and electrons, and perhaps something exotic. But basically, that's what you have. And at the very early times, the energy density in radiation, we'll look at that in a second, was by far the dominant energy density. At some point, that changed. But for a while, there was still an ionized plasma. And I will go through all those things after the break in the next lecture. But at some point, those electrons and protons, they started combining. Because the universe cools down, it expands. So as you expand something, it cools down. It's just expansion cooling. And as the universe cools, at some point, the photons does not interact with the baryons long enough anymore. And on the first thing is that the photons become too cold to ionize hydrogen. So electrons and protons, getting a bit confused here. Electrons and protons join together and create hydrogen and helium. Then after a little while longer, photons cannot interact with baryons very much. So they're not going to be able to boss baryons around. And after that, it's where matter and radiation evolve separately in the universe. And that happened at a redshift of about 1,000. And that's the furthest back you can see. This is basically an optical depth of 1. Beyond here, you can't see anything.
Sorry, so
yeah.
The scale of time is in C value?
Yeah, so here it's in terms of redshift. It's in terms of scale factors of the universe. So here the universe was 1,000th of its present size. Okay. Here is 150th of its present size. It's a convenient thing because this is fairly model independent, but converting it to time in years depends on cosmology, and it's a bit more uncertain. So I stayed away from it. But this part, there's basically nothing interesting happening. So here is where the first galaxies form, and after that, galaxy formation really kicks off. So the picture that we're going to flesh out and explain much better during the course is essentially this, that the universe is built up essentially by halos of dark matter. So dark matter produces the scaffolding on which we build the universe. Okay? So dark matter kind of crashes together. It makes lots of clumps. And most of the mass of the universe, more than 50% at least, is in these halos, these dark matter halos. I'm going to talk about them a lot in this course. So later you will see what they are in more detail. And in those halos, you will also have baryonic matter. And then some baryonic matter fall in here. Now, if you have a mass of something that's just moving, you can always associate a kinetic energy to it. Okay? You just use a virial theorem, you can relate the potential energy and the kinetic energy, and you can derive a temperature. So it's typical temperature. And so when baryons fall into these dark matter halos, they will be heated by a shock. And that shock, the typical temperature, will be about the temperature of the virial, this kinetic energy of the halo. So the gas falls in, gets heated up, and so to be able to form stars, that gas has to cool down. And that's what happens slowly inside here. And that happens differently depending on the size of the halo. And that's going to be a crucial fact for later understanding differences between low mass galaxies and high mass galaxies. But to do that, we need to go into the physics of cooling, but we'll do that later. And so when that temperature is low enough, then what happens is that these baryons, they fall in, they have some angular momentum, most of them anyway, and angular momentum isn't radiated away by photons. So what happens is that they cool, and cooling means they collapse in towards the center, but they'll still have some angular momentum, and that's why most galaxies are going to be formed as disks, as something that's rotating. If they had no angular momentum, what you will get is they will all go, and you get a black hole. That would be exciting, but very boring to live in. So that's a crucial thing, star-forming disks. Okay, so that's the cartoon picture. That's the overall framework that we're going to work with. Now, that picture is catchy, but it doesn't quite work like that. So when people have run simulations of this process, what they find is that actually it isn't as simple as that. So if it was that simple, what would happen if I calculate the temperature of the gas and let the gas fall into these dark matter halos, it heats up, as I said, to the temperature of the halo. Okay, easy. So if I look inside that halo, it should be the same temperature everywhere, right? That should be easy peasy. And so this is a figure of that. This shows the temperature colored from blue to red, where blue is cold and red is hot, or yellow is, I don't remember whether yellow or red is the hottest. But and so what you see is this is the size of the halo, the dark matter. And this is the temperature of the baryons. And you can see the baryons more or less have the same temperature in this halo. But those are kind of similar to what's outside. It's not a big difference. And then you go to a smaller halo, and the smaller halo, you see it isn't uniform inside. It actually has these streams of cold matter that's going inside the dark matter halo. And so it's not all heated up. And that's actually quite an interesting result. It's not trivial. Part of the reason is that when you have something that goes into a shock, if it's dense enough, it's going to be protected. You're going to affect the surroundings, but the rest inside is going to be shielded. But this is dependent on the mass. So that's going to be another factor that's going to tell us what happens with different masses. And there's another thing which I haven't talked about yet. It also depends on what's forming inside there. If you form a black hole, and if you form massive stars that explode as supernovae, they will explode and they will give off energy to the gas, and they can push the gas out again. And so here are different simulations with different ways of treating that process. It's an AGN where you can see where it's a black hole in the center, and it's heated up the central part quite a bit. If it's only stars, it might be quite cool in the center. So these processes are very important for understanding what's going on. And where this really becomes important, and this we will come back to, I'm just giving it as a taster to make when we come back to it later, a bit clearer. What we will calculate later in the course is the distribution of mass in dark matter halos. It's a classical result, goes back to Press and Schechter from 1974. And they calculated, and we're going to see how that works later in the course, the number of halos as a function of their mass from 10 to the 8 solar masses to 10 to the 16 solar masses halos. These are really big. There are not very many of them in the universe. These are very, very common. Okay? So this whole process we will want to do so that we know how to do this. It's quite remarkable that just a very simple argument based on statistics can give you this functional form. And so you think, oh, that looks kind of right. There's a power law. It kind of goes down there. Looks about okay. Until you compare it against what the galaxies look like. And that's this. Okay, I've done two things here. One is that I shifted the dark matter one because it was over here somewhere. So I moved it back here. But that's okay because there's more dark matter in the universe than there is baryons. So I just moved that. But the important thing is the galaxy mass function drops off much quicker, and it doesn't go up as fast. Okay? So it's crucial. It's different in a specific way, and you can turn that around. You can take. So we think that each halo has the same amount of same fraction of baryons. Okay? There's some fraction of baryons in the universe, and each dark matter halo should have its share. So if I divide this one by that one, I get the efficiency of galaxy formation. Okay? How efficient is a galaxy, or how efficient is a halo in turning baryons into stars? Okay? That's what you care about. Now this particular plot, which is quite famous, is unfortunately is inverted the y-axis. So you turn your heads upside down, you can now follow my argument. But here's the mass of the galaxy. Here's the 1 over the efficiency. So where it's the minimum here, it has the highest efficiency, just to be confusing. And what you can see, this is the universal baryon fraction. Okay? It's about here. It's a bit less than 1/10. So. And here, you see that, firstly, you see it everywhere. Halos are not efficient at turning baryons into galaxies. That's the first thing to notice, because it doesn't go down here. It's actually far away from turning all the baryons into stars by a factor of almost, 6 or 7. Okay? So galaxy formation is inefficient. It's probably a little bit surprising. You would think, okay, you've put some baryons in, should turn into stars. There's no particular reason why it shouldn't. So why is that? But the other striking thing is that it's very inefficient for high-mass galaxies. And it's also very inefficient for low-mass galaxies. In fact, the Milky Way, in breach of the Copernican principle, is the most efficient. Right? It's plonk in here. That's where the Milky Way lives. Yeah, we are the pinnacle of galaxy evolution. Now, why is that happening? Okay, that's also crucial to understand, of course. And the arguments have generally been that there are two reasons for this, and they've both been given the name, slightly obscure name of feedback. So when astronomers, galaxy formation people don't understand something, they're most likely to say, oh, it's just feedback, which means they don't know, but they'll have a word for it at least. Now, what we think is happening is we think that you form lots of massive stars in a galaxy. Those stars explode, and they give off a wind, or they give off they interact with their surroundings. So the idea is you push all that energy out from supernovae, you put it into gas, and that gas will be, pushed away or heated up, pushed out of the galaxy. And this is actually what we can see in some galaxies. This is a nearby galaxy called M82. It's a famous one for this particular issue. The galaxy itself is kind of irregular. The stars are shown in green in here. For some reason, I'm yet to fathom people like to use green for stars, given that no star in the universe is green. I don't know why that's chosen, but anyway, green is stars. The blue is hard X-rays. So very, very hard X-rays from massive stars, supernovae, explosions, all kinds of exciting stuff that I don't know anything about. And that all happens here in the central part. That's where there's a lot of star formation. There's been many supernovae in this galaxy over the last few million years. And that all happened in the center. And then what that center is doing is that it's blowing out what's called the super wind, because super always sounds better. So it's a massive wind of gas that's being pushed out from the central part. And that's traced by this red stuff here, which is, again, this hydrogen alpha, this Balmer line, recombination line, is tracing it. Or in this case, in this particular plot, it's also, again, X-rays, but low energy X-rays. If you plot this with hydrogen alpha instead, it looks very much the same. And so that's gas that's being pushed out of the center. And we know that happens, okay? And some of that gas is going to disappear from the galaxy completely, okay? So if you do that well enough, you get rid of the gas in this galaxy.
This is, well, is scale.
This is just, this circular one is basically, it's taken from a paper, this paper that's cited there, and I think that circle was basically to define what they call the central region of the galaxy.
This one, this green disk.
Oh, the green disk.
No,
Yeah.
not in the center, but...
Oh, this one. Ah, yeah, that's a foreground star. So, so all the green bits here are foreground stars, but this one is saturated in the image, so it's basically looks awful because of that. So it's not, it's nothing to do with the galaxy. But yeah, I could have cut it away, I guess. So okay, so that's one process. That's when stars push gas away. So you could think if this goes on for enough, you just go, you blow off all the gas out of the galaxy. Okay, but it isn't very efficient. So that's why people have also suggested another thing, and that's AGN feedback. Okay. So AGN feedback is when you have an active galactic nucleus, and AGN is when you have a massive, supermassive black hole in the center of a galaxy, and you feed it gas, and as a thank you, it radiates massive amounts of radiation out. Now, we know that when you have that, you get these big shells being blown out. This is not from galaxies, but from clusters of galaxies, so much more massive. And we see these shells, you can see some of them here, being blown out. And we think they have to do with overpressurization. You add a lot of pressure, and that's blowing these bubbles slowly out of these galaxy clusters. Now, we think something like this happens in galaxies too. And it's been postulated now for probably a decade that this is crucial. The problem is we don't really understand the process. We can see it happening, but we don't know why. Not very well anyway. And why couldn't we only do it with stars? Well, in theory, you probably could do it all with stars, but it would be a bit weird. And so the reason it would be a bit weird is that if I start on this side, okay, I have a dinky galaxy, you know, kind of irrelevant galaxy, and I form a bunch of stars, and I say, okay, it's not difficult to get enough massive stars to give off more energy than the binding energy of this galaxy. And that's fine. And then I go up, and the binding energy increases, and this feedback effect goes down, which is a bit strange because you get more and more stars, so it should at least be constant. It isn't. And then suddenly it changes sign, and it becomes more and more efficient again. And there's nobody has ever been able to come up with a sensible theoretical explanation that can do this non-monotonous trend with stars. If it just went that way, you could do it with stars, no problem. If it just went that way, you probably could do it with stars with a lot more problems. But to do it like that, no chance. So we think there has to be one process here and one process here. And that's why we have the two ideas for feedback. One that we understand kind of-ish, supernovae, and one that we don't so much understand, active galactic nuclei. So that's usually what we say. Okay, this is why these two mass functions look different. We think, okay, here they're different because AGN feedback gets rid of baryons, and hence you don't form stars. And here we say it's exploding stars that are going to get rid of baryons, and hence you form less stars. So we'll look at that in a little bit more detail later. So those are really the, I'm a little bit early. These are really the main things I wanted to bring home to as an explanation of what we really wanted to understand in this course. Okay? So the first thing is, so what's the origin of the mass function of galaxies? We'll do it in two steps. We will start with the mass function of halos. And that we will cover, I think, not to complete mathematical satisfaction, but well enough. And then we will talk about why it differs from the galaxy mass function in more detail than what I've done now. Another thing which is quite a recent result and still is under study is really to understand why the star formation rate of galaxies and their stellar content are so closely related. And so there we will try to review what people have developed, and we try to develop our own simple model for this. And that echoes some of the work that people have done in the last 4 or 5 years, something like that. So there we will really get quite close to state of the art of what's going on. And that's also related to what's the physical reason for the redshift evolution of this relationship. And finally, towards the end, I will try to discuss why disk galaxies have the sizes they have. So why aren't galaxies all the same size? Or why aren't galaxies, why is there a relationship for sizes? Why do galaxies have a particular size? And it belongs a little bit together with this, why do galaxies have a particular mass? Why aren't there galaxies in the universe that's 10 to the 14 solar masses? You might not know, but there aren't any. Okay? The biggest galaxy we know today in terms of their stellar content is 3-4 times 10 to the 12 solar masses. There's no believable galaxy that's more than 10 to the 13 solar masses. On the other end of the spectrum, there are galaxies that are 10 to the 4 solar masses. There are galaxies around the Milky Way today that are fainter in absolute magnitude than the brighter stars in Orion. Right? There are galaxies that are absolute magnitudes of 2. Okay? That sounds a bit crazy, but they can be really, really small, but they cannot be really, really big. And that's a puzzle. Okay, so I actually came to the end of what I had planned to talk about in this lecture, a bit earlier than I thought, but if
I hope that they start to
yeah. Yeah. Yeah, no, so right now it's, we just touched on, I've just told you about observations, but I hope afterwards we will actually interact a bit more. Does anybody have any questions about what I talked about? Or what I didn't talk about?
Ahora el strip.
¿Cuál es el cuásar? Los cuásar por lo general son asociados a los AGNs, a las galaxias de núcleo activo, ¿cierto? ¿Cuál es, por ejemplo, el cuásar más lejano observado? ¿Qué relación tiene esos objetos tan masivos y tan energéticos con, por ejemplo, la formación de esos objetos en esas etapas primarias.
So, so what's the relationship between? Okay,
yeah.
well, you can explain. I think I
Quasars
was it.
are earliest structures, so objects
Yeah.
formed in the early age of the universe. So, and
Yeah.
the first question was about the mass, which is the most massive quasar that we can found, and yeah, and
Yeah.
y que tan viejos son.
Yeah. So okay. So let me
The massive and the oldest.
yeah. Let me go backwards. Start with the end. So that's an interesting question. Okay. So today the most distant or the oldest the first objects we know in the universe are no longer quasars. They're actually galaxies. So the highest, the most distant galaxy we know today came out now in middle of July. And that's at redshift of the new ones all the time. So I never remember. I think redshift 8.6. So that would be less than 1 billion years after the Big Bang, quite a bit less actually, 300 million years I think after the Big Bang. So that's a galaxy in the sense. So, but maybe it's best that I explain what the difference is or similarities of it, because if let me see. So it doesn't have to. The only reason why we talk about quasars is because they're very, very bright, so it's easy to see them. So let me draw a cartoon version of a galaxy. Okay. So if I have a spiral galaxy, most spiral galaxies have a black hole in the center. So okay. So in the Milky Way, this is the black hole. It's about 10 to the 6 solar masses. And a black hole on its own is very faint. The only radiation that, if you have nothing around the black hole, the only thing that escapes is what's called Hawking radiation. It's extremely faint, and you can't see it at all for a black hole like this. So around this, you need to get gas into it. So the Milky Way's black hole is very faint because there is no gas falling into it. Now, if you now I looked at this galaxy from above, but let me go in and zoom in now on the black hole. Okay, so I have the black hole here, and around this black hole, we think there is an accretion disk. So this is gas. And this is fueling this black hole. That's basically what the accretion disk is doing. There's a gap around here because if you have had general relativity, you remember there is something called the innermost stable orbit. At some point, matter cannot stay there. It has to fall into the black hole. Doesn't matter so much. But this fuel, this fuel, will lead things into the galaxy. And on a bigger scale, we think there is what's called a torus. So, and that might be related to this one. Doesn't really matter for our argument. Okay, so you have the torus. I'm not very good at drawing, I'm sorry. Yeah, it's like a donut with a hole that goes around the black hole. And so this is very efficient. Okay, if you put a lot of gas into the center and you have a black hole there, it just gets eaten by the black hole and it radiates out again. Now, so if you have your black hole here, you have your torus. what happens is that if you look at this galaxy from here, you don't see it because the torus is in the way. And we call it a type 2 AGN, if we at all understand that it's a AGN. But if you see it from here, whoops, then you see more or less directly into the central engine, and we call it a quasar. And so what seems to happen is that these black holes, so the brightness and the luminosity of the quasar is proportional to the mass of the black hole to some power. Okay. So you put more mass into the black hole, it gets brighter. But it is also dependent on how much gas you can feed into the black hole. So both of those things need to be there. So early on in the universe, the reason why we see quasars really far away is because there was a lot of gas around a lot of galaxies, and they all seem to have formed black holes very quickly.
So they grow very quickly.
They grow very quickly. So it's not clear why these black holes grow so quickly. We don't really know, but they must have grown very, very fast.
Puedo preguntar. Y se queda-
Pues las primeras estrellas fueron muy masivas y digamos la evolución de estrellas de esas masas supone fueron a
Okay.
Mm-hmm.
That maybe the reason for this quickly growth is because the first stars was very massive and evolved very quickly to it.
No, that's a very good question. Okay, that's a very good suggestion. It doesn't. The reason it might be true. Okay, the reason why it's a bit difficult to use this is that when we talk about these massive stars, we talk about 400 solar masses, 500 solar masses. They're very massive. And when they explode, they're thought to explode as what's called pair instability supernova. And they don't leave a black hole out afterwards. They basically just go bang. There's nothing left.
Collapsing core.
No, there's no collapsed core. They explode due to pair instability in the core, and the core is blown apart. So there's really nothing left if the stars are like that. They might not be. Okay, if they're not like that, then yes, the first stars might leave black holes, but you still need to have lots of gas to fall into it. And it needs to fall in and not make a disk, right? If it falls in with lots of angular momentum, well, works quite well. So maybe they are the first stars explode, and the stars that live in halos that don't spin, okay, some halos don't have a lot of spin, maybe that's where you can then get lots of mass going into the center, forming this black hole quickly, and you get, these are the first quasars that you see. We don't know, but that's a possible way. So it's very likely that the stars, the first stars, are the seeds of black holes, but we don't know.
How this could happen? That a supernova explode and it didn't let anything.
So it depends on what happens in the center. So in the sense, well, it's not very clear what happens in the supernova explosions in the first place. But in the pair instability of supernova, what happens is that I don't remember actually what happens, but the main energy generation, basically due to pair instability formation, is really in the center. So you get all the energy generated in the very center, whereas in the core collapse scenario, you have already basically the energy is more than enough to lift degeneracy. Whereas in most of the other scenarios, what you do is you have a degenerate core and you have fall back onto the degenerate core, and then that degenerate core just continues to collapse into a black hole or a neutron star. Whereas in this case, you basically have so much energy generation in the center, you lift degeneracy, and then you blow it all apart, and there's no fall back in. So it depends on that energy balance. Yeah.
This question maybe has to do with something you will talk about later in another lecture. But when we talk about the difference between the mass function of dark matter halos and the galaxy mass function, does this difference have to do with the way we understand gravity?
I will not talk about it. I will talk a little bit about it in my public talk, but not in this course. So that's a very good question. It's actually not easy to explain all the aspects, but what? How should I say this? Okay, so we have quite a lot of models for how gravity might change, might differ from general relativity, and so you could come up with can come up with a something to do with the modification of gravity that could be very different and could explain something like this. That's fully possible. But the problem is it wouldn't fit other observations. So if you want to modify gravity, but also satisfy all the observations, like we have binary pulsars, we have the perihelion of Mercury, which moves, which is a test of general relativity. We have the cosmic microwave background. There's a lot of different tests we have on general relativity. And if I want to modify gravity and satisfy all those tests, then the effect on this mass function is quite small. It's, see if I might even have the plot here. See here. Of course, I'm not going to find it now. Nah. Okay, I'm not going to find it right now, but basically the effect is of the order of 20–30%. Okay, so you can change gravity, but it will not be an order of magnitude, which is what you need. So it's not big enough. But in that case, you would have to have something. So typically, we call those f of r. So if you have had general relativity, you probably have heard about the Ricci scalar or the Ricci tensor. It doesn't really matter. If you haven't heard about it, it doesn't matter. It has to do with how curved the universe is. And so you need to have it so that gravity is changed differently on different scales. So you would need to have something that changed gravity a lot on very big scales, and not very much, and then not very much in intermediate scales, but then a lot again at small scales. And that would be very contrived. And on these scales, when you come down to 10⁶ or so, then we actually can test gravity very well, because we can really look at what goes on in our galaxy. So it's very difficult to explain this particular discrepancy. But it is actually proposed as a test of gravity. So to test whether the universe follows Einstein's general relativity or whether it is something else, people have looked at this green curve here, the halo mass function, and see how that changes. And so it is a relevant question. It just won't explain this difference, but it is still an interesting thing to test. Okay, so we do use it.
More question?
No? Yeah? Oh, so that's an excellent question. I didn't talk about it, and I won't talk about it very much. So there are two reasons. But firstly, it does. Okay? So in the solar system, most of the dark matter is in the center of the sun. Yeah. So people have actually looked at that and tried to understand what's the effect of dark matter on the evolution of the sun. And it's very small. But then people looked at higher the very early universe, and this goes back to the question about the first stars, and there is actually space to make stars that are called dark stars, where most of the mass in those stars are dark matter. And they're really weird. And they could, in theory, exist in the center of the Milky Way as well.
Mixed.
They're mixed, yeah, it's baryons and dark matter.
Stars made by a mix of dark and baronic matter.
Yep. Very weird. And so what they look like is basically a normal star, but puffed up. They get blown up a lot. Now, to really do what you're saying, okay, so you really cluster it and clump it, more than that, you need to have what's called interacting dark matter. So at the moment, what we think is dark matter basically is point particles, and they go swish past each other. They don't feel anything. And we are pretty sure that they don't interact with electromagnetic radiation, because otherwise we couldn't see through the universe. But if dark matter is a clump of something bigger, then they have a cross section and they can collide. And they can collide and they can clump. They might do. It's actually, actually I will actually come a little bit back to it later in the course, but in very, very small galaxies, when we look in the center of them, they have a lot of dark matter. And it's very hard to explain why they have so much dark matter if dark matter doesn't interact. So it might actually clump together, and then these dark matter particles might not be point particles, but they might be conglomerates of something. And so they have they're much bigger cross sections for collisions, and that's that. And so then they might collide, but otherwise they don't clump very much because they're only affected by gravitation. So that's why there is some in the sun, because there is gravity. But if you want them to really clump, they need to lose energy. And there's no way of losing energy from just gravity. Well, there's gravitational waves, but they're not very efficient for this. So you need something that can clump and then cool, send off a radiation somewhere. That's when you can clump things really well. And so the current way of doing it, we cannot do that with dark matter, but they might be interacting and then they might clump more. We don't know. So it's not ruled out. It's just a lot more difficult when you let it do that. So we don't do it.
Okay.
Yeah.
Question?
Yeah.
Okay. So now I think it's time for a break.
Yeah, I think so too.
Put the first slide with the
yes, that's
web
right.
direction.
Thanks for...
So I just want to remember you that all the problems to solve will be there.
Yeah.
At that website. And tomorrow and Thursday at 9, including Friday too.
Yeah.
Jarle will be at the office, at my office, to attend your questions about the problems, okay?
Yeah.
So
that's actually quite important for the people that actually will be doing the hand-in problems in particular. Whoops, careful. In particular, the problems are not easy, okay? You are all smart, and so it's a bit challenging. And next week I'm on holidays, so I'm not going to answer emails very much. So I would strongly recommend that those of you who are doing the hand-in problems to start looking at them this week and use this hour in the morning to pick my brains about the problems. Okay? I'm not going to give you the answer.
I want to remember that tomorrow we have seminar at 1 o'clock. It's what a technical seminar. And at 6:30 we will have the public talk at the planetarium tomorrow. Okay? So Wednesday. Yes, tomorrow. Tomorrow 6:30 at the planetarium there will be the public talk, okay? So tomorrow is a busy day.
You'll be really sick of my voice.
So after lunch, we will wait for you at 2 o'clock.
Yeah. Sounds good.
back here. Okay.
Bye-bye.
So see you later.